accept that. I hope that you are getting that. Can I get a thumbs up from anyone? Yes, perfect. Okay, so welcome everyone to this methods at constants, link lab constants workshop. So this is the second workshop in the series for 2022. We had our first workshop in February, March, and that was on forced alignment for phonetic research by Dr. Patricia Strikarczuk from Manchester. You can watch that from links that I will be posting in the chat later, but all the recordings are available. And today we are very happy here to have Christopher Kenyon with us talking about digital signal processing in R. And so this workshop will take place today and tomorrow. And I want to give a very short introduction to this idea of the methods at constants workshop in general, and then I will introduce Chris, and then I will pass the floor to him. So we are at the Link Lab in Constants, so this consortium of laboratories in linguistics. We are organizing a series of open access, sort of open everything workshops. So there are 3 workshops on methods in linguistics that are being recorded, and the recordings will be available for everybody in the future, and materials as well. So, you know, if you have students that, you know, in a year will ask you more about digital signal processing, you will be able to find this recording and send it to them. The goal is to have, of course, workshops that are about cutting edge methods in linguistics and quantitative research. We want, of course, this the workshops are primarily organized here at the university for internal staff at the university, but as you can see, they're open to everybody. So we are happy to see so many people here. We have 2 more workshops planned for 2022 and 1 that might be happening in 2023. So of course, as you know, we're doing digital signal processing today and tomorrow. In September, we will have more about exploring text data online using R, so creating, you know, corporal data from social networks like, you know, Twitter or Reddit or YouTube comments, and how to sort of analyze and get around, like visualize and analyze that data. This workshop will be taught by Dr. Lisa Donlan, who's a postdoctoral researcher in Manchester. We plan to have something on cluster analysis and by Dr. Eleanor Shodroff, and then something about Bayesian analysis for speech science later on in 2023. I will post the links to the constants page down here, and you can have a look and sort of keep track on where things are happening. And I usually post on our Twitter account, where you can, you know, find the links to signing up for these workshops. So this is just what I wanted to say about the methods at constants workshop series. And so now I would like to briefly introduce Christopher, who is the speaker for the workshop for today and tomorrow. So Christopher Kenyon is a lecturer in speech sciences at UCL, so University College London. He obtained his PhD in French linguistics from the University of Illinois, and then was a postdoctoral fellow at the University of North Carolina, and scientific staff at the LMU University in Munich. He is, as he will tell you later, I'm sure, is interested in everything articulatory phonetics, uses a lot of different methods, both experimental methods and quantitative methods, to study phonetics and articulation, and we will see how, I suppose, digital signal processing can be applied to many of these methods. He has published in an array of outlets and prestigious outlets at that, including the Journal for the Association of Laboratory Phonology, Journal of Phonetics, Acoustic Society of America. He has a very well-curated website with a lot of links and photographs that he takes, which are quite nice. And I think you bonus follow him on Twitter for lots of pet photos and cat photos. So that's always good. And so thank you, Chris, for running this workshop, and I will just let the floor to you. And so Yeah, and you will also tell us a bit more about the questions and kind of how that works during the workshop, and we'll deal with that. Thank you.
Awesome. Thanks, Max. Super excited to be here. Really excited to be part of the workshop series, which I think is fantastic. I want to just give a little bit of an introduction, sort of a background to kind of what my goal for this particular sort of workshop is, because it may be a little bit different than kind of the format of other workshops that you may attend. So we only have 4 hours over these next 2 days, which is not a lot of time. And so I think that the best way to sort of like give you, your best bang for the buck here is to kind of do the format that I've proposed, which is the main part of the workshop is the tutorial document that you should have already had access to. And to get the most out of the workshop, I'm assuming that everyone has a background in R and is also at least made yourself familiar with the tutorial document, because how the workshop is actually going to run during these 4 hours is I'm going to go through, not the entire thing, because there's a lot in there, far more than we would do in 4 hours, but go through some of the main bits. And in that, we can talk about some questions you may have. I can do a little bit of live coding with some of changes and address things that come up, and I hopefully this kind of format should work for everyone. So that being said, I also want to give a background to what the goal, like why am I doing this? So DSP in R, what is the point of this particular workshop? My background is actually, well, my programming background is in MATLAB. And as many of you may be familiar with MATLAB or use MATLAB, that's sort of kind of like a go-to for a lot of signal analysis and DSP work. So why are we doing this in R? Well, kind of in the spirit of the workshop series itself, I have really tried to personally, both in my personal life and my professional life, make a move towards more open source, open access software, methods, everything. And in that have moved more, moved away from doing most of my work in MATLAB because of licensing. So then the question is, well, in our field, R or Python? And I do have a background in both, but I have far more background in R. And most importantly, as many of you, I do my statistical treatment in R. And so this sort of like brings up the concept of kind of keeping it all in the same environment. So a typical workflow might be doing some sort of analysis that you're interested in, the actual primary analysis in a language like MATLAB or Python, or even doing acoustic analysis in Prot, and then taking the data in some form, importing it into R in a way that maintains everything and it's safe and you haven't lost any data, and that in and of itself, as we know, can be problematic, and then doing your data wrangling and your stats there. But depending on what you may want to do, you don't necessarily have to do that. Actually, most of the work that I do now, from the bottom up, I've collected the data and I actually process the data and wrangle and do my stats. I do it all in R. So that keeps everything in one environment. It's an open source language. It's much easier to replicate, and it's much easier for me to keep everything sort of in line and making sure that none of my data has been lost in translation or something like that. So what the workshop is going to be then is in that spirit. It's going to be, again, assuming that you have a background in R, so I'm not going to be teaching you R. Also, I'm not going to be doing really, really advanced DSP work, but what we're going to go over is some fundamental techniques and issues that arise in this kind of signal analysis, things that I do use in my day-to-day work, and how to do that in R. And we're going to try to stick to the base R language as much as possible, because as I explained in the tutorial document, I think this is the best way to really get to grips with the language and using your data. So that being said, we're going to go ahead and start off everything then. As far as questions are concerned, how we're going to do this is, if you have questions, go ahead and put them in the chat window. As soon as I share my screen, I'm not going to be able to see the chat window, but Max is going to monitor that. And at any point, if multiple people are having the same question, or if there are things that are especially pertinent, then Max, you can just interrupt me, and then we can go over those at the time. Technical issues as far as getting some package to work, or something that is having a problem with not the technique itself, but R, that is another reason for giving the tutorial document a week ahead of time. So hopefully those things should be worked out coming due today. So those kind of technical issues this is not the domain for that. But anything that comes up, any questions that you have about the techniques or the analyses that we're going to be doing, then certainly go ahead and put those in the chat window. I think that's everything I wanted to mention as an intro.
Yes, can I jump in and just add a couple of very, very brief things? So firstly, I will be posting in the chat a link to a Slack channel that I have created for the methods series in general. There should be, or there will be, a channel for this workshop. And so this will be a completely unmoderated place. So neither Chris or me will be there. So it's not a place to ask questions in real time. But I found it's a nice place to kind of either discuss this thing among yourselves, or after the workshop, remain in touch or ask questions to people that have attended the workshop, be in the loop for future workshops. Of course, this is a completely optional thing, but it's there. We've done this starting for the previous workshop, and some people have posted questions and ideas, even weeks following that. So I will post a link, and you feel free to join it if you want, but it's not going to be moderated during the workshop. So don't go and post questions there unless you are expecting your sort of course mates to help you answer that. Finally, also before we start, I also wanted to thank Shun, who has been helping setting up the workshop and doing a lot of the work to get you all informed with your links and to get all the information to you ahead of time. So a big thank you to Shun for that. And that's me. So back to you, Chris.
Fantastic. Thanks. Right. So let's go ahead and get going, because we've got a lot to get through, and I want to try to get through as much of it as possible. So here we go. I'll go ahead and move all this. So hopefully there should be no blank screens. Right. Okay. So like I said, you've got the tutorial document. That's the main thing that everyone really needs to go through if you haven't done that already. But what we're going to go to, what I have shown here is not the R Markdown document that I used to create that. They have the crucial bits of code that I want to go over as we go through. And this just makes it easier for me to kind of do that. So first things first, there are a number of packages that you're going to have to have installed, and I have these listed here. There are 8 of them. Now, I personally, my habit for coding is in R is really, as much as possible, to not load the packages. I try to keep everything as explicit as possible, which means that I will call the specific package namespace within the code itself. The only one that we're going to load here is I'm not even sure how to actually pronounce this, Magritte R or Magritter, or I'm not really sure, but this gives you our handy piping function. I do want to take the time to note that as of R 4.1, there is a piping function that is now available in base R. This is what the now base R pipe function is. So you don't actually need this to do your, you don't need this, which we're going to use to do your piping. But we're going to go ahead and load it here, use this because most people are familiar with this. So the other thing is I have a function here that my attempt, my idea is that hopefully that this would be easy for people to access the data. So the tutorial document, if you find it helpful, if you want to share it with people, if you want to come back to it later, I have things stored in my Dropbox, so the data should be available indefinitely. So you can actually, you don't have to share the data, you can just share the HTML document, and then anyone can access the data by downloading it. Now, a couple of things have come to my attention. One is that why this works fine on my system and not others, I have no idea. But if you are not able to get the download function to work for some of the data, the first thing to try is to take off the secure tag here. So instead of HTTPS, try HTTP, okay? Hopefully that should work for you. If all else fails, if this doesn't work, if you just look at the code here, you can probably get a sense of what this is doing. We're pasting together the elements of a link. We're getting the binary representation of that link and then writing that to a file. What this means is that if none of this works for you, if this function itself doesn't work for you, what you can do instead is simply create that, that download link yourself. So the two arguments here are the actual random identifier key here, and then X is the name of the file. So if we do this, where if we look at this first data set that we're going to be working with, the name of the file, X here, is Emma EMG data RDA, okay? And then this is the unique key. What this means is that the download for this is actually just, it's just this, right? So we've got that, and then the key here, okay?
Hi,
So
Chris, could you, sorry, could you zoom in a
that
little bit? Because the
should now hopefully then work for everyone, regardless of whether or not you can get this actual R function to download the data correctly to your working directory. If all else fails, if none of that works, you can recreate this download link yourself. Simply put that into your browser, and then you just download the link, right? Okay, so hopefully this should work. We're going to use, I'm assuming that this will work for everyone, so we're going to use this function throughout the tutorial. The other thing is that I'm going to play some audio. In R, you have to tell R to associate an audio player in your system with being able to play the audio. So you have to tell it where that is located, the directory for that. So this is for my system in Linux, it's aplay. Oops, why did I get no? Okay. I'm not really sure why I have that error there, but it linked successfully. So I've got my player linked. For other operating systems, I gave in the tutorial document ones that I think may work, should work. I haven't tested them. But if you can't get the audio to play on your own computer, not a big deal. I'm going to play the audio here. All right. Okay. So that being said, let's go ahead and jump into actually working with some of the data. So this first day,
Chris,
we're going to work with one-dimensional data over time. Tomorrow, we're going to work with two-dimensional data, primarily MR images. So today, we're going to work with a number of different types of one-dimensional data, but we're going to come across some concepts that are crucial for any type of analysis where you want to look at time-varying signals of this sort. So we're going to go ahead and download the first set of data and then load this in the working directory. And if that works for you, you should now have in your workspace this EMMA EMG data list. So we look at this, get a summary of this. We've got a number of things here. Importantly, in here, we've got the sampling rates. So we've got a sampling rate for, we've got 3 different types of data in this data structure. We've got an audio signal. We've got some EMG, so intramuscular EMG signals from both the lateral pterygoid and the medial pterygoid. And then we have some EMMA data as well. Each of these were recorded at a different sampling rate. And a sampling rate is simply defined as how many samples were captured per second. So that's the definition here, is numbers per second. And this is going to be crucial for then creating plots and doing some analysis to compare, for example, an audio signal at a given point in time with an EMMA signal at a given point in time, or the EMG signal at a given point in time. We're going to first listen to some audio just to get a sense of what we're dealing with in this data. To do this, we're first going to create a sound object as samples, and we need data for that. And we also need to assign then what the sampling rate is. Well, that is all available for you in this data set. So we've got the sampling rates that are in this field, and then you can tell the length of these, given that we've got some pretty large data here. These are the actual the data samples. So if we plot one of these, for example, G audio a little bit of time because we got lots of samples here.
Chris, can you hear me?
It's taking more time because I have Zoom going. But yeah, we've got a waveform here, and we can tell we've got some silent portions, and then we've got some speech. So let's go ahead and listen to what that speech sounds like. Hopefully you should hear this on your end.
Asasa.
Now I'm not hearing it on mine.
Apepa. Afafa. Asasa.
Can you hear that on your end? Or do I need to play that again? Because I had to make some audio changes on my end. Can someone give me a yay or nay?
We could hear it.
Yes.
You can hear it? Okay, cool, nice.
But Mass was trying to say something. I think that the our studio is too small. Maybe increase the font size.
Oh, sure.
Yes, I don't know whether, I think like because you switched the audio, you couldn't hear us for a while. So that was what's going on. I tried to interrupt you a couple of times, but you couldn't.
Oh,
you
yeah.
didn't seem to hear me say something.
I couldn't hear anything. No, I should be able to now.
Okay, great. Yes.
Okay, cool. Is that font is better?
Perfect, thanks.
Great. Okay, cool. So yeah, let's go ahead and play that again.
Now we can't hear it.
Yeah, I don't know what's happening. I think it's there we go.
Asasa. Olola. Apepa.
Okay, so you get the idea. We've got nonce words here and very, slow laboratory speech. And the idea behind this this study is we're interested in what is the role of these two jaw muscles in speech. How do they coordinate in speech? So we've got some nonce words. We've got some EMG data. We also have some EMMA data for the actual movement of the jaw. And if we look at, there's also, let's do. There's a field here called segments, which if we take a look at this, it should be pretty clear what this is. We've got some SAMPA conventions here for these nonce words. So we've got the word, we've got the individual phone segments, and then importantly, we've got some time points in seconds associated with the beginning or the start and the end of each of those phones. So this is the kind of thing that we're, anytime you do some sort of signal analysis, especially if you are comparing two different types of signals, which many of you may be interested in. So, for example, audio and EMMA, or audio and EMG, or EMG and EMMA, or whatever, you need to be able to relate a time point in real time, in seconds, to individual data samples. Well, because these equipment were recording at different sampling rates, what that means is we have to find a way to translate one type of data to the other as far as time points are concerned. What this means is that if we, for example, plot out this audio signal, but then if we were to also plot out, let's see, I don't know, let's do, what do we have here again? Let's do the lateral pterygoid. Okay. Now, you can see here the number of samples that are listed. If we go between the audio and the lateral pterygoid, we have a different number of samples. Same amount of time, different number of samples, simply because there are different sampling rates. So this is something that everyone has to deal with when you're doing signal analysis. So in order to be able to compare one type of signal or another, we need what the sampling rate is for that. Because we're going to be using this a lot, the easiest thing is to simply take those numbers and then make some variables out of them. So here we've got the audio sampling rate, which was 22,050. And now we've got, we're going to plot some audio against one of the jaw signals, so from the EMMA data. The EMMA sampling rate is quite a bit smaller, right? So the EMMA system was not sampling as many digital points per second as the audio. So there's no way that we can plot the two together or compare them without first converting the time points to relative samples. Okay, what this means, so if hopefully you should be familiar with this concept, but if you're not familiar with this concept, what this means is that, so again, sampling rate is number of samples per second. So if we take a time point exactly 1 second, right? So from the start of recording, exactly at time point 1 second that has lapsed or passed since the beginning of the recording, in the audio channel, we have 22,050 data samples. But in the EMMA channel, we only have, well, this is not a round number, but the closest then is 100 samples, okay? So this is the concept of sampling rate. What this means is that in order to get the nearest sample in whatever the signal is that you're dealing with, you simply have to multiply the sampling rate by the time point in seconds. Now, this is really, really crucial. This keeps changing here. This is really crucial that it has to be in seconds because, again, the definition of sampling rate is number of samples per second. So if you're dealing with data where your time point is in milliseconds, for example, you have to keep this in mind when you are getting your nearest sample to a time point. You have to convert this to seconds. Okay. Now let's go ahead and do this then for, let's look at, the first word that we're going to look at is this word, afafa. We're going to look at this because this gives a nice movement of the jaw that we can get some really, some interesting patterns that we can look at. Well, in the segments field, these are the time points and that are associated with these 5 phone segments for this word. And we can see that they start at row 16 and they end at row 20, okay? So we're first going to plot the audio signal for just this word. What we need to do then is find where in the audio data is the sample that corresponds to the starting time point, and then where do we have the ending time point? Well, one issue is that if we then, so the starting time point then is the 16th index of this column start. Okay, so that's the starting point of the word. Now I said we just have to multiply that by the sampling rate. Well, that's not entirely true, because when we do that, we get a non-integer value. Okay, we have a numeric value, but it's not a whole integer. Digital samples are whole integers. Now, R does some under the hood. If you were to actually try to access this sample number, you're actually not going to get an error. It's going to work for you because it's going to round. But I don't want to trust that. I want to make everything explicit, so we're going to do that here. So all you need to do then is simply round whatever these values are. Okay. So we're going to then assign these to some variables. So we've got T1 for time point 1, T2 for time point 2. So then if we take a look at these, now we have some nice integer values for the sample, the audio sample corresponding to the beginning of the word, and the audio sample corresponding to the end of the word. Okay. Well, this is nice because what we can do then is in R, so you should be familiar with the concept of, so there are 346,925 samples in this data, and you can plot, you can do anything, whatever you want with a subset of that. So if you only want to analyze then, for example, I don't know, the first 1,000 samples, you then do in square brackets 1 to 1,000. Okay, so those are the first 1,000 samples, and we're going to do a line instead of, yeah, that is easier to interpret here. So those are the first 1,000 samples. Well, you can do that with any range of samples. We already have a range of samples that we're interested in, time point 1 and time point 2. So since those are now variables, instead of 1 to 1,000, we're going to do T1 to T2. So this is going to plot then samples, not 1 to 1,000, but samples 159,764 to 179,450. And there we have a word, right? This is our afafa. So there's the waveform of the word. And we're going to also go ahead and take the Sampa notation for that word and make that into a variable. So we've got our afafa. We can then reuse that if we want to. And let's go ahead and then add that into our plot. So we plot this, and then we can programmatically add into the title, audio signal for word, and then whatever our word is. So if we want to then, we're dealing with something else and say, I don't know, banana. When you plot this, then it's going to say banana, right? But we don't want it to say banana. We want it to be afafa. Okay, cool. So we've got the audio signal. So we want the goal here for this first bit of the exercise, we want to compare the audio signal to a jaw movement signal. And we want to then also compare specific points of time within the word. We've got those. We've got the beginning and end of all of our phone segments. So let's go ahead and then make these into some variables as well. So basically, we're going to do the same thing that we did before. But instead of just the beginning and the end of the word, we're going to do all of the time points for all of the segments and then make that into 6 different variables. So we're also going to, instead of just calling these all the time, let's go ahead and then take those segments for the audio and then for the EMMA, and let's go ahead and then save those. So we're going to do everything that we've just done, but we're going to have a range of samples. So if we do this, we've got, well, let's actually just do this. So we have a vector of numeric values in this audio segment, or this audio seg sort of object, from 159,764 to 179,450. So those are the samples for the entire word in the audio data. Similarly, for the EMMA data, we've got much smaller numbers, but it's the same concept. So samples 725 to 815 correspond to the same points of time, but for the EMMA data. Okay. Now, here's where we get to something that is really crucial for any type of analysis that you're doing here. So again, we need to compare. So what we're going to do is we're going to make a plot where we have two different subplots. We have the audio data, and then we've got our jaw movement data. Well, we already know that we don't have the same number of samples. So you can't just plot one and then the other, because if you do that, one's going to be much longer than the other, and it isn't going to make any sense, right? You can't actually make any sort of interpretation of that. So instead of plotting on the x-axis the number of samples, we're going to plot real time. So in order to do that, a handy function in base R is this sequence, the SEQ, the sequence function. What sequence does is allows you to make a numeric sequence from any start point to any other endpoint. So let's make a sequence of numbers from 100 to 200. And we can either do it by increments of, I don't know, whatever we want, 5. Okay, so we've got that there. Instead of telling it the number of increments, we could also say, I want you to give me this number sequence, but I want you to specifically make the vector a certain length, right? Certain number of numbers. We can do it, do any more, you can do 1,000 and you get really, really small increments. You could just do 100, you could do 10, you can do, whatever you want. This function will then give you an equal increment between each number in the series, okay? So you probably see where we're going to go with this. We're going to make two different time vectors, one for audio and one for EMMA, from the first time point to the second time point in seconds. And the length of that vector is going to be equal to the length of the data. Hopefully that makes sense, okay? What this means is that these time series vectors are going to have different lengths for the two different audio signals because we have different sampling rates, we have different number of samples, but the time points are going to be comparable between them because we're going to start at the same real time in seconds, and we're going to end at the same real time in seconds, okay? So if we do that, then starting from time point 1, this time point in seconds, to time point 6, this time point in seconds, you can use the same function and you can do a length of 15 or a length of 25 or however many you want, okay? Well, what we're going to do is the length is going to be equal to the length of the data. So when we plot one against the other, R will let us to do that. We can plot 1,000 samples against 1,000 time points, for example. And we're going to go ahead and make these into some data frames for our plotting. So let's first, we're going to pre-allocate a data frame for each of these. So for the audio, we're going to have a column called data, which is going to be numeric values that are going to be as long as our data. And importantly, a column named time, which is also going to be as long as the data, right? So they have to be even. These are what are called rectangular arrays. So if we do that, we pre-allocate that, and we should then do a head on that. We just have zeros, right? But we've got zeros with as many number of rows as we have samples in the data, okay? We can then fill that in with then our data. So now if we look at that, we no longer have zero values. We have actual waveform sound pressure values. And then the time we're going to fill in using this sequence function. So again, from a time point in seconds to a time point in seconds with the same length as the number of data samples that we have. Okay. So now we've got our data, and then we've got time points associated with that. One thing as well, just a really quick thing, it's really important when you're working with, you know, DSP kind of stuff like this, is to understand the relationship between all of these things that we're working with, time and samples and sampling rate. And a nice way to then sort of kind of bring that home now is we can then, now that we've created these time series, we can ask the question, well, what is the increment then between one sample and another? We can do that by example, just using the difference between audio time, or no, just 1 and 2. So the first 2 samples gives us, that is the increment. Well, we take the inverse of that, lo and behold, that's our sampling rate. Well, it's rounded, but it's very, very close to our actual sample rate, right? Because our sample rate is 22050, right? So the inverse of, so, you know, this is the same kind of thing if you're looking at a waveform of audio and you're talking about the period of, you know, a glottal cycle. The inverse of the period duration is also what, so the inverse of the period duration is the frequency, right? So we're working with the same concept here. Okay, we're going to do the same exact thing. Now we're just going to use it for the jaw data as well. So we can see that we've got a similar type of data frame for the audio that ends at the same time point, but at a different number of samples. So we only have 91 rows in this data frame, whereas we have almost 200,000 rows in the audio data frame. But now we're all set up for actually plotting the two against each other because we have these time series. I'm taking the opportunity in the workshop to also introduce a series, well, a package that many of you may not know about, might find interesting, called Plotly. We're not going to use ggplot here. I'm assuming that everyone is familiar with ggplot. We're going to use Plotly because I'm assuming that not all of you are familiar with it, but might find it interesting because you can interact with the plots in ways that you can't with ggplot. One of the issues, though, is that it's not as fleshed out as ggplot. So we're going to have to kind of recreate the wheel a little bit here. We're going to add some vertical lines to some of the data. So I've created a function that allows us to do that in an easier way. So you can see that Plotly kind of looks similar to ggplot in the sense of that we have to build a base object. And then whereas with ggplot, you would add in different components or different layers on that. Here with Plotly, we're going to pipe one to the other, but it's kind of a similar thing, right? So we're going to create the base plot. On the x-axis, we're going to have time. On the y-axis, we're going to have our data. We're going to then add into that the actual lines for the waveform of the audio. And then we're going to add some vertical lines for all of our 6 time points. So we'll go ahead and save that then as an object. And we can view that object just like we can with ggplot. Now, you'll probably notice something that might be interesting, might be different, is that this didn't open up in the plots tab. Now, ggplot and base R plotting are going to open up in the plots tab. Plotly is going to open up in the viewer tab. Why? Because it's interactive. You can put your cursor here and you can get the actual information that you want. You can zoom in. You can, do some data, at least, some checking things if you want, or, getting some numbers to write down or whatever you want. And then you can double click here and zoom back out. So these are things that you can do because this is an HTML document. So this is not unlike ggplot, which will then create what's called a rasterized graphic. I think it saves it as a PNG, and it saves that in a temporary folder. You can't then do anything with that, right? You can't interact with it. Plotly, you can interact with this because this is HTML. If you save this as an HTML document, you can then put it on your web page, You can create a tutorial with this. And in the you may have noticed in the tutorial, you can do this directly in your browser as well. So you can zoom, you can get whatever data you want. You can do all of this interactive work that you can't do with ggplot. So we got that for our audio, and we're going to do the same thing then for our jaw rotation data. So this is the signal that we're going to look at, is how the jaw rotates open. So now that we have these two plots saved, we're going to use this subplot function to, as you guessed, put them together. So now here we have, I'll make this a little bit larger. We have then our audio data plotted on the same, well, two different subplots for the same figure with the rotation data. And they're both now plotted against the same time course. So even though there are far fewer samples in this jaw rotation data than there are for the audio data, they are now time aligned because we've plotted them against these time series objects. And you can now zoom in to both of these, and we can get a really good indication of how the jaw rotates open for this word. And we get some nice sort of patterns that we can begin to at least qualitatively discuss, things like the jaw starts rotating open in about the temporal midpoint of the vowel, reaches its peak right at the onset of this f fricative. Right. Okay. So that I don't think I did have an exercise that we're certainly not going to have time for. But on your own, it would be good for you to try to do this exercise. So you've got the general ideas here, right? Importantly, you need to be able to plot data against a time series object that is of the same length as the data. We've done that now for the audio and this jaw rotation data for this word afafa. And so then I have an exercise here that you can on your own do the same thing for the audio, the jaw rotation data, the vertical, so the X dimension of the tongue tip sensor, the lateral pterygoid signal, and the medial pterygoid signal, and put those all into one plot. To do that for a different word. So obviously this takes time to do. This is something that you can, you're free to do on your own, but we don't have time to do this now. But you can see where there are a certain number of things that you would need to change in order to reproduce this plot. But once you have this plot, again, this is an HTML object or document, I guess, file, okay? And so because of that, you can then do these nice sort of interactive things on your website, or sharing the, if you're collaborating with some people and you want to share some preliminary results, you can just share this HTML document with them. They can open it up in their browser. And actually, if we do, can I just, maybe I can't. Try it, there we go. Can I? No, I thought I could just open this up separately, but I can't. Oh well, okay. Anyway, yeah, so time on your own, try to recreate this plot using the same techniques that I just showed you. And again, this is, really introductory kind of thing here, but what we've just done in needing to convert a time point to a specific sample in the data, and creating a time series object to be able to compare two different data streams is bread and butter type stuff that you'll always need to do, no matter what the language is. And again, no matter what the language is, it's going to be a similar type of process that you would follow. Right. Okay. So I guess now would be a good time to stop and see if there are any questions.
So in the chat, we're fairly fine. I think mostly
some doubts about technical things, but participants of the workshops are being very supportive, and so most of them are being solved as we go along.
That's fantastic. That's really great. Thank you. Cool. Any questions about some of the concepts that we've gone over here, or Plotly? I'll also add there's some really cool three-dimensional applications for Plotly, so you can create a three-dimensional graphic, and you can pick it and rotate it in your browser. So you could, for example, if you've got EMMA data and you've got, or OptiTrack data or whatever, of like a face, it's very good to orient what that looks like in 3 dimensions. So you can use Plotly to do that, to create these sort of these HTML files to then share with people that can actually then in their browser click and zoom and rotate the face around and that sort of thing. Again, things that you can't do with ggplot, obviously.
Miriam in chat asks whether you could share the R script directly. That would be easier to maybe follow along.
So the pertinent bits of the code are in the tutorial document.
Yeah, I know, but it's just easier to follow along and do it at the same time while you're explaining it, instead of going back and forth.
Oh, you mean, so you mean this actual thing that I'm working with here, the R code for workshop?
Yeah.
Yeah.
Yeah, cool, thanks.
Yeah. Is it best to just do that now, or I'm not really sure, Max?
What do you mean? You could just post it in the chat, I think, and whoever wants to.
Oh, can I do that?
I think, yeah, you can. You should be able to just drag it from your whatever folder.
Fancy.
That is in.
Ooh, fancy! Look at that. All right, here we go. Ooh. All right. Good.
Cool, thank you.
Cool. All right, so that's basic stuff, but important concepts that we're going to then bring on into some of the next stuff that we're going to do. Now, so we're halfway through the first day already, which is crazy. The second half, I'm really excited about this because we're going to continue working with one-dimensional data, but we're actually going to, instead of just plotting it, which is important and this is really useful, we're gonna do some real manipulation. So we've got a goal here, and we're going to actually do some, not analysis, but we're going to do some actual signal processing with this. So for this, we're already going to load the data set that we're going to use tomorrow, which is MRI data. So if you go ahead and download that and then load that, you should now then have a second data set in your workshop called MRI data. Okay. Tomorrow, we're going to use, well, let's first do a summary of this. So there are 3 fields here, data 1, 2, and 3. Data 1 and 2 are going to be for tomorrow. Those are, we've got audio in there, but we've got important actual images that we're going to do some image analysis techniques with tomorrow. Data 3 is just audio. So that's what we're going to work with today. And what we're going to do with this is to try to, if you've ever worked with MRI, you know it's really difficult with speech because of this scanner noise, right? So we've got some audio. You can see that there's something in there, but much to our dismay and very loud compared to that speech is this omnipresent scanner noise, right? And what we're going to do is a technique called spectral subtraction to try to remove this from our audio. So what I've just used here is, so this, I cannot recommend this package highly enough. So this package, Phone Tools, just has lots of really great stuff that is immensely helpful. And just it's worth taking some time to really kind of look at everything that's in there. But we're going to use a couple of different functions from this package. The first one is generating a spectrogram, which we've just done. Now, you may or may not be familiar with this color space, which is sometimes referred to as jet. But this is a color space that's really good for differentiating different levels of values, like for the amplitude values in the spectrogram. But we don't have to plot that with that. We can use different colors. We can also take the colors off and make this something that is closer to something like you'd see in plot. So we can do that by saying colors equals false. So now we have a black and white spectrogram. We can also change things like the dynamic range and then also the maximum frequency here. So if we look at, so I've gone ahead and I've already created an object here for our sampling rate of the audio, but our sampling rate here is 16,000. So we've had different sampling rates for the first data set. Yet we have now a different sampling rate, 16,000. So the audio for this was recorded at 16,000 samples per second, which means if you are familiar with digital sampling in what's called the Nyquist limit or the Nyquist frequency, you can record as much frequency information up to half of your sampling rate. What this means is that the Nyquist frequency for this recording is 8,000 hertz. So let's go ahead and get all of the information in the spectrogram that we can, which is up to 8,000. So we're going to do a couple of different things here. We're going to, we're going to do that. We're going to make our maximum frequency equal to 8,000. And let's also change the dynamic range. So we're going to do something that's as close as possible to something that we would see in Prot. So here, when we plot this, we've now got our spectrogram of all of the frequency information, which is great because now we've got some fricatives here, which we couldn't see before. We've got a dynamic range, which is really similar to what we have in Prot, and we can fully see the issue here. These huge bands, right? So we've got lots of noise here that's always there throughout the entire recording. And what does this sound like? Well, we're going to use the same kind of function that we had before, using the data and the sampling rate associated with the data. We're going to play this.
This is an example of what noise reduction can sound like.
Horrible, right? So that really loud buzz, we can hear my speech in there, but we've got this huge amplitude buzz that we need to get rid of. Now, it turns out that the actual the spectral structure of that is really complicated. So how are we going to remove that? So that's what we're going to do for this second part of the first day of the workshop, is a technique that is used more or less to some extent for a long time to get rid of noise in signals. Now, to do this, we're going to do a couple of things first. We're going to first just going to take one sort of chunk of this audio, and we're going to go through the concepts of what spectral subtraction does. You could probably, you already know because you've gone through the document, but even if you hadn't yet, the name itself kind of gives you an indication of what we're doing. We are subtracting something in the spectrum, right? So we are doing spectral subtraction. Well, what does that really mean? So the key part there, spectral, means that we need to generate a spectrum. Well, you may or may not already know this, but if you're familiar with Fourier Transform, that is how we get a spectrum, right? So we are dealing with an audio signal. Well, this is from before, but same kind of idea. We have an audio signal, which is sound pressure variation over time. What we want to do is to get frequency information out of that. Well, in order to do that, we need to do a Fourier transform. In the Fourier transform, you need to have a window length. So we need to first decide how much of the signal at a time are we going to consider for taking that pressure, that time varying pressure signal, and then getting phase and frequency information from that. A very common window of analysis for FFT is primarily because this ends up being very fast because it's a base 2 number, is 1024 samples. So we're gonna go ahead and use that, and we're going to use that as our we're gonna have a variable FFT length, so the length of our FFT to do that. So we're going to let's take a sample of our noise here, right? So we've got some speech, but we can see that the speech doesn't start right away. What this means is that we've got a portion at the beginning where there is no speech, but there is scanner noise, right? So we can even look at that. So we can say, we're not going to plot all of the audio, but let's just do a spectrogram of, for example, I don't know, the first 1,000 samples, let's say, or let's do, I don't know, 4,000. So we can see here we're starting to get speech at the end, but in the first, probably 3,500 samples or so, we don't have any speech, right? We just have scanner noise. Okay? We're going to use that. We are going to use that knowledge of the signal to try to represent what that noise or how that noise can be characterized. And we're going to do that using our FFT length. So let's take sort of a chunk of that audio of the first 1024 samples. So we have that now that we can plot this, and sure enough, that is not silence. That should be silence, right? That in the sense of nobody's speaking right now. We're not interested in anything else that's going on. We're speech scientists. We're interested in speech. We want this bit to be silent. It's definitely not silent. That's super noisy, right? So we want to get rid of this. So this is what's called our noise profile. And if we do an FFT of that, so if we do a fast Fourier transform, we get an object that we're not gonna spend the time to really get into this, but an FFT will give us it's what's called a complex series. So we've got a real component and we've got an imaginary component. And what this allows us to do is extract from this the real component can be then made into frequency information, and this imaginary component we can take the angle of this and get phase. So a spectral Fourier transform will give us frequency and phase. Now the frequency can be extracted using the modulus function. This is essentially just the absolute value. We can kind of consider it that way. So if we plot this then, so this is we've done our FFT. Now we've extracted the absolute value of this real component. And if we plot that, hey, a spectrum, right? So now we've got a spectrum of the noise, but something looks weird here. We've got two different spectra and they look the same, but they're flipped, right? Again, we're not going to spend the time to get into this for this workshop, but this is always going to happen when you do an FFT of a real signal, right? So what I mean by that is not a complex signal. If you take a real signal like a waveform, you do an FFT of this, you're going to get what's called conjugate symmetry. And we don't care about what's going on up here because, again, we can only use the frequency information that is half of our sampling rate. So we only care about what's happening in this first half of the spectrum. So let's go ahead and just plot that first half of the spectrum. So we're going to take that magnitude, so our frequency information, we're only going to plot the samples up to the Nyquist limit, which is our FFT length divided by 2. So half of our, in this case, our sampling rate. So we've sampled only 1024 samples. And then up to half of that is the frequency that we're interested in. So if we plot that, now we've got a spectrum of the noise. We can see that it's really complex. But like the first part, like the first exercise that we did, we're not actually interested in plotting against the number of samples. So that's what index is here. So index is just literally telling you how many samples there are, right? From the first one to the 100th to the 200th, all the way to up to 500. We've got 512 total here, right? We don't really care about that. What the information, we want to translate this information here, not to time, like we did in the first exercise, but to frequency, right? So that's what the spectrum tells us is on the x-axis is frequency, on the y-axis is amplitude. Well, we're going to do the exact same thing like we did to create a time series object, except we're going to use the same technique to create a frequency series object, right? But we're going to do the exact same thing using this sequence function. We're going to make a numeric sequence from 1 hertz up to half of the sampling rate. So the Nyquist limit, okay? And we're going to make this the length of the data that we're interested in, which is again, half of our FFT length. So here, and hopefully everyone followed that. So just like the time, from time point A to time point B with a certain length, we're doing from frequency A to frequency B with a certain length. So this now gives us a numeric vector of frequency bins. And just like we did before, we can find the frequency, not the time resolution, but we can find the frequency resolution, which is going to be the difference of, for example, first 2 samples. So each bin represents about 15.5 hertz, right? So each time we have a new sample, we've increased by 15.5 hertz. So now that we have that, we're going to recreate this plot, but instead of plotting against number of samples, we're going to plot against hertz. Also going to give some labels to our axes. Okay, so this is now our spectrum of the noise. We can see that this is super problematic for speech, right? All of this information is like 500 hertz to 6,000 hertz. Well, that happens to be like the crucial frequency range for speech, right? And we've got all of this complex, high amplitude, well, varying amplitude harmonic structure within that range. And that's obviously a problem if you want to analyze that speech then. Okay, what we're going to do is now that we have a baseline spectrum of the noise, right? So we have our noise profile. We're going to subtract that from the actual noisy data. So we are assuming, so there are different ways that you can approach the concept of what we're doing here is noise removal, or you'll also see this as a speech enhancement for our purposes. There are a number of ways of approaching the concept of noise removal, and we are assuming the concept that a noisy signal is what's called additive noise, is a clean signal plus noise, okay? That may seem simple, but it's really not, and that's not the only way to approach noise removal, but it's the way that we're using here. What this means is that if we consider, I actually have a really simple formula of this in the tutorial document. So if we have a noisy signal, yn, so n being any time index here. So if we have a noisy signal y, and we consider that S, our clean signal, plus D, our sort of degraded, our noise, right? Well, what this means is that this is what we're given, right? So we are given the noisy signal. We have a recording that's come from the MRI scanner that is clean signal, me speaking, plus noise, the MRI scanner doing its thing. that is combined together in the real atmosphere when it's recorded. Okay, we are given that noisy signal Y. We want to obtain the clean signal S. If we assume that the noisy signal Y is additive function of clean signal S plus noisy signal D, well, we can then obtain an estimate of S by removing D from Y. Make sense? Okay. Well, we have now an estimate of D. We have an estimate of the noise profile of the scanner. So we then remove that from the noisy signal. That's the basic concept behind spectral subtraction. Now, I have a lot of hedging here because it turns out that it's far more complicated than that. It's actually really complicated to accurately estimate what the noise profile is, in part because it can be constantly changing. So even in this small bit that we're looking at of the noise profile, we can see, for example, it's changing in amplitude, it's pulsating, right? So we've got high amplitude, low amplitude, high amplitude, low amplitude, right? So it's pulsating here. So these are some of the reasons why it's, this isn't going to end up being perfect, but we're going to get a really, really good estimate of S by just removing this, this estimate of D from Y. Okay, so let's get, we're going to grab a chunk of the noisy signal. I've already, I've chosen some specific, a range of 1024 samples because this is right at the transition in the word this, right at the transition between the vowel I and the fricative S. So if you look at the spectrogram of this chunk, what we want to see is some low frequency information associated with the vowel, followed by high frequency information associated with the fricative. And we see that, but we've got all of this banding from the noise that is just overriding all of that, right? So we want to remove that and retain that that base spectral information for the speech. Okay, so let's do that for just this chunk here. So we're going to do the same thing as we have just done for the noise. We're going to do a fast Fourier transform. We're going to get the magnitude of that using the modulus function. And now if we then plot this against our Hertz, our frequency object, this is now the spectrum of the noisy signal. So if you're thinking about what the goal is here, somewhere in here is the frequency information associated with the speech. Somewhere in here is the frequency information associated with the scanner. We want to tease those two apart. And just to visualize what that means, here is our noisy signal. Now I'm going to overlay on top of that our noise profile. We can see that parts of those line up. We want to remove that blue from the red. That should, in theory, give us an estimate of the underlying speech, right? Well, let's just do that. Literally subtract one from the other. We're literally just going to subtract the spectrum of the noise here, mag 0. We're going to subtract that from the spectrum of the noisy signal, right? That's this here. Exactly what we have here is what we're estimating here, okay? So we do that and then plot this. This is our results. So we subtracted one from the other. And I'm going to add on here. So we have a red line. What does this red line indicate? Well, so this is where you can already see it's spectral subtraction in theory seems like the solution to all of the world's noise problems, right? We just subtract one from the other and you're good to go. Well, we've already come across one issue is that it's actually really difficult to properly estimate the noise profile. And the other issue is, well, I mean, I guess related to that is that when you do the spectral subtraction, well, everything above this line, all of our positive values, we're assuming that is speech, right? Because we've got the amplitude of speech combined with the amplitude of the scanner. Those two together are going to be louder than either one individually, right? This is, we're assuming an additive function here. So if we subtracted one from the other, anything that is positive residual, we then assume is speech. What about these negative values? So this is where this does get a little bit tricky. In theory, if we have a perfect estimate of the noise component in this time window, then these zero or these negative values should never happen. If you have perfectly estimated the noise and subtracted that from the noisy signal, you should never get negative values. Well, we do have negative values. That's problematic. So we're going to work with the theory that we shouldn't have negative values and just make those zero. Okay. So we're going to take anything that is negative, we're going to make it zero, plot this again. This is now our estimate of the underlying clean signal, right? And we can already see, we compare this to, let's go ahead and remove this. Remove this. Right. Okay, so here's our noisy signal. Here's our estimate of the clean signal. And again, we're looking at this transition between the vowel and fricative. We should have low frequency information and then this high frequency information that should be sort of more or less, because it's a fricative, it should be more or less randomly distributed across the frequency spectrum, but in high frequencies. We don't have that with the noisy spectrum because we've got all of this junk that's in the middle band. Now we have that. We've got low frequency harmonic information associated with voicing, right? You see that we've got some nice, clear harmonic structure in low frequencies. Then in high frequencies, we've got energy that is, you know, fairly randomly distributed. That looks like a spectrum that we would expect for that time window, okay? So that is the main part of what we want to do here is that we've subtracted one from the other. We've zeroed out the negative values. Now, remember that a Fourier transform of our goal here is to get back to a waveform. We started with a waveform. We want to remove noise information and get back to a waveform. Well, we first had to take that waveform, do a Fourier transform, which gets us 2 dimensions of information. So the waveform, we have time and we have amplitude. The Fourier decomposition gives us frequency and phase. We've now manipulated the frequency. We need to take that information and get back to time and amplitude to get the waveform, right? Well, in order to do that, we need both of those original components from the Fourier decomposition, frequency and phase. Here's our frequency. Here's our estimate of manipulating the frequency domain. So we have our frequency information. What do we do for phase? This is another area of noise removal, the whole field of noise removal that is super complicated and people are, you know, constantly working on this. How do you properly estimate the phase? It's really, really difficult. What we're going to do is, for the sake of just keeping things simple, we're going to use the original phase of the noisy signal, right? So we've got some phase information there, which tells us how do the individual cosines then relate to over time. That gives us our time information. It's really difficult to estimate that properly, so we're just going to use the original phase. We've done all of our manipulation in spectral domain. We're going to take our original phase, we're going to combine the two together and do what's called an inverse fast Fourier transform. Okay, so we've got our original phase from the FFT of the noisy signal, and we can get this using, so the modulus function gave us our frequency information. The argument function arg gives us our phase information. So that's now saved as an object, and we can plot this, but this is going to be nearly incomprehensible. It's just really, really complicated, right? So what this means is that over time, how does the different, so if you think about the spectrum, so this spectrum here, so how, for each of these frequency bins, what is the phase of that, of the cosine associated with that frequency? And that then gives us our time information. but we have different time informations for combining all of the different frequencies. Okay. We also need to convert back to, so we have the Fourier transform gives us a complex series. We need to create a complex series using the phase and the spectral, the frequency. And to do that, we need to create an imaginary number. So complex series imaginary numbers in DSP are simply tools. That they're tools that allow us to then do things like put into one number the concept of two dimensions, right? So we're just using this as a tool. So J is going to be an imaginary number, which is the square root of -1. Well, square root of -1 doesn't exist in the real world. That gives us an imaginary number. And what we need to do then is, so I've given here the math for you. This will create our complex series by taking the imaginary number and multiplying it by the phase, taking the exponent of that and multiplying it by our new estimate of the spectrum here, right? So we do that, and then if we do an inverse Fourier transform on that, and lo and behold, we now have what a very close representation of what we're really looking for. We have the low frequency information associated with the vowel, followed in time by this high frequency information associated with the fricative. Okay. So before we move on, I'm going to ask if there are any questions about the fundamental concept of spectral subtraction, what we're doing here, because what we're going to do is apply this concept. We've done it for one window of 1024 samples. We're going to then apply that to the whole audio chain, the whole audio signal, to then get a denoised signal over time. But before we do that, I first want to stop and ask if there are any questions about the concept of what we're doing here. Don't see anything in the chat.
I guess if I could ask real quick then,
Yeah.
I know it may be too complicated, so if it is, just skip over it. But the phase recovery is just for, I guess you could think of where it starts on the y-axis. Is that correct, or do I have that way off?
Yes. Well, yeah. So it's super complex, and I'm not going to be able to explain it really well because one, it's complex, and two, I don't actually understand it that well. But what a Fourier decomposition does is so conceptually, if you think about, for example, like a DCT, a discrete cosine transform, it's actually really similar. So what the Fourier transform does is it assumes that any signal, doesn't need to be periodic, it can literally be any signal at all, can be decomposed into a sum of individual simple sine waves, right? So that's the fundamental sort of idea behind Fourier analysis, is that any signal can be represented by a sum of simple sine waves. And those sine waves will have frequency and amplitude, and importantly, a time relation, that's phase, right? So in order to do that, the Fourier analysis maintains that information. So we've got what I'm calling the two dimensions of information is really four, I guess, because the spectrum is the actual values are amplitude, and then as you increase different indexes in that, it gives you frequency, right? Well, the phase gives it tells it is the relation between the different frequency values and time. So if you were to shift that, the simple sine wave associated with that frequency, if you were to shift that in time, you would get a different additive waveform, right? So you can take two different sine waves and add them together and get a completely different complex sine wave if you shift one of them in time. So the Fourier analysis will tell you if you were to take all of these sine waves and shift them in varying degrees throughout the sine function, right, and add them together, you would get this original waveform. Does that make sense? It is a way of relating the frequency information to time.
Yes, that's much more clear now. Thank you.
Yeah,
And
cool.
You may be getting to this, but I guess how much will we be able to see, I guess, hear this audio reconstructed so we can see what got deleted out?
Yep, exactly.
Okay.
Yep.
Cool.
Yeah, we're going to do that at the very end. And this is a simple concept, the idea of just taking a spectrum and subtracting another spectrum from it. But I think you'll be pretty pleased with how well just this very simple technique works. We've got another question here. Can you explain again why removing anything below 0 in the subtraction, keeping those above? Yeah. So this all has to do with the fact that it is nobody in the world has come up with a way of perfectly estimating the noise, right? That in and of itself is a whole field of research, is how do you estimate the spectral information of noise? It's always going to be imperfect. If you can imagine, if you had, right, so again, let's imagine the situation. I'm sitting in the scanner and I'm speaking with my vocal tract. That then has an effect on the local atmosphere that we call sound, okay? Now, I'm speaking to you now, and you can hear me having that local effect on my atmosphere around me, and you are perceiving that as sound, and there's no other noise happening around me, okay? Now you put me into an MRI scanner, and suddenly that effect that I have on the atmosphere as sound is now added to the effect that the scanner has on the atmosphere, which is the noise. Now, if you were to perfectly know at any given time point, you were able to perfectly estimate what the noise of what contribution the scanner makes to the overall sound. And if you were to remove that, you would perfectly get my voice with no other contamination. Now, what that means is that in theory, if you take the spectrum of the perfect spectrum of the noise and subtract that from me speaking along with the noise, you would never have any negative values. You would only ever have 0 and positive. But because we can't perfectly estimate what the scanner noise is at any given point in time, we do end up with negative values. What we're doing here is we're accepting that as a fault of our field at the moment. And you first of all, you can't do an FFT, you can't do an inverse FFT if the spectrum has any negative values. So we have to do something with those. One thing is just to shift everything up. You could take this spectrum. Oh, I deleted it. So you could take where are we at? No. You could take this spectrum and basically do a baseline correction and shift everything by the lowest number. So basically shift everything up by something like here, right? So that will give you no negative values, right? That ends up not working well at all. You get a really gross, noisy signal because really this information shouldn't be here. So the best compromise that we're going to make is, instead of baseline shifting everything up, we're just going to work with the assumption that we shouldn't have any negative values in our ideal world and just make those 0. Does that make any sense?
a short question.
Mhm.
So we don't want any negative values because in the real world it's not possible to have a negative frequency values in our
Well, if you
right, because our vocal folds cannot. Oh, what is the thought behind that?
Well, the thought is, so if I do, hopefully this should give me an error. So if I do, so here I have what I've just done is the spectral subtraction as is. Now I've got some negative values in here. And if I then try to, we take our phase information, we have our complex number. If I now try to then make a complex series with that, oh, it doesn't give me an error. It will allow me to do it. But it's gonna, I have to think about this. I'll have to think about this and maybe get back to you in the Slack channel or something. In theory, I didn't think that you could actually do an inverse FFT with any negative values, but it looks like we're allowed to do that. Well, we could check it with this end result and see what happens if we don't make those zeros. It's an empirical question. We can actually look at the result and listen to the result. Well, yeah, remind me, we'll come back to that in a bit. All right, so good. I think we'll go ahead and move along just because I want to be conscious of time here. But the idea is that we want, so we've done this for one window of our FFT length was 1,024 samples, right? So that gives us only 64 milliseconds of information. Well, that's cool for those 64 milliseconds, right? But we're interested in the entire audio signal, right? So what we need to do is do the same thing throughout the whole signal. Now, one thing that we could do is literally just do it for the first 1,024 samples, then do it for the next, and then do it for the next. That's perfectly possible. This ends up providing a very, very bad result because of something that's called spectral leakage. So the FFT, so how FFT works is so it's like, it's assuming that within that window that you can recreate the sum of signs in that window, but a sine function has no limit, right? So this is a finite window in time that we're looking into, and we're now decomposing an infinite series, okay? What happens then is if you have information that is at the edges that is non-zero, you can get an incorrect estimate where the FFT has assumed the fact that my first sample here is a non-zero value means that it was part of some sign function that began before. And if you add that together, you end up getting very bad results. So what we want to do is what's called tapering or windowing. So this is something you'll come across multiple times, all over the place for signal analysis. You'll see it when you do Foreman analysis. In prot, you very often do things like choose what your window is, a hand window or a Hamming window or whatever. This is because under the hood, the prot function is applying some sort of tapering to the signal before it does a spectral analysis. So we're going to do the same thing, but we're going to do it in a little bit different way. There are multiple ways to do this. I'm going to show you one and explain why I'm doing it here. So the idea is that we want to do the same spectral subtraction for the whole audio signal. So we're first going to just pre-allocate a vector that is the same length as the original audio signal. And that length of the audio signal is here, so 64,542 samples long. We're going to then create, we're going to pre-allocate a numeric vector here called cleaned for obvious reasons. That is of the same length. So cleaned is just a bunch of zeros again. We're going to fill in those zeros with our cleaned wave information, right? After we've done spectral subtraction and then the inverse Fourier transform. But again, we're not going to just take a chunk and then move on to the next chunk and move on to the next chunk. What we're going to do is we're going to take a chunk, do the analysis, then we're going to move only part way down and then take a new chunk of audio that overlaps with the previous one. Then we're going to taper the two, and I'll show what I mean by this, do the individual analyses of both of them, and then add the results together. This ends up giving us a much cleaner result than if you were to just do one and then do the next and do the next, because you don't have any spectral leakage. So what we're going to do is the most common way of doing this sort of overlapping movie window is to simply overlap by 50%. So instead of, we're going to do the first one at samples 1 through 1024, but instead of starting then the next one at sample 1025, we're actually going to start at sample 513. So halfway into it. And I'll show you why specifically 50%. The reason is that we're going to, for our tapering, we're going to use what's called a hand window. So a hand window is defined by this function here. And if I plot this, this is what a hand window looks like. This may look familiar to you. And you don't have to memorize this function because again, our nice our font tools package, we can generate this using a number of different types of windows. We're going to do this with a hand window, and we see that we get the exact same thing. Now, why specifically a hand window is because I'm doing specifically 50% overlap. Well, what do I mean by this? How are the two related to each other? So in taking these overlapping portions, what I'm going to do is taper the first portion down to 0, and then the next portion, I'm going to taper it up from 0. What this means is that I'm going to split this shape, this window, which is also called a kernel. I'm going to split this kernel in half. I'm going to take the second half is going to be the first tapering function. It's called a half hand window. The second tapering function is going to be the first half, right? So let's go ahead and do that. So now I've got the first half hand kernel is going to be the second half of the handing window, or the hand window. And the second one is going to be the first half, right? So hopefully this will make sense when I plot them. So this is now our tapering function for when we have these overlapping portions for the first half. So we're tapering, it's unfortunate. Oh, there we go, good. So this gives us a window that starts at 1, tapers down to 0. If you multiply this by some signal, what this means is that the very first sample is going to be the actual value, right? So it's just multiplying by 1. And then in this cosine function manner, it's going, well, this is a quarter cosine. It's going to then taper down gradually until it gets to 0. So the very last sample will be exactly 0. And then this cosine function taper between them. The second one looks the exact opposite, right? Now, why have I done it this way? Well, because of how the handing window operates, so this is what's called a raised cosine property. If we take these two halves and we add them together, that's the purple line, we get 1, exactly 1, all throughout the entire range. So what we're doing is we're going to take when we have an overlapping portion, so we've got two different FFT windows and they're overlapped by exactly 50%. So that's 512 samples. We're going to take the 512 samples from the first window. We're going to taper them. We're going to do the spectral analysis. We're going to then taper the results by this function. We're going to do the second window, taking the 512 that overlap with that. We're going to multiply it by this tapering function here. Then when we add those two together, we've gotten rid of the spectral leakage problem, and we get the original amplitude that we want. That's the additive property here of these two halves of the hand window. Gives us exactly 1. So just as an example of what I mean by tapering an audio, like actually the audio function here. So if we got, I'm just going to take the first 512 samples of our audio, and if we multiply that by this first red line, we get audio that starts at its original amplitude and then tapers down gradually to 0. And then same thing, if we take that and then multiply it by the second half hand window, we start at 0 and then taper up. And if we were to add those together, and 2 times chunk, we get, now let's do lines chunk, the original signal, the exact original signal. Okay, so this is what we're going to do. So it's not going to be the exact signal, because what we're doing is we're moving throughout in time. So we're doing one estimate, and then we're moving with 50% overlap and doing another estimate. Then we're going to take the overlapping portion and then do this additive, this function here, which then deals with the spectral leakage issue. So we want to do this throughout the entire signal. So we first have to know how many windows of 1024 samples, considering that they're each going to overlap by 50% throughout, how many can we fit into the entire file? So this will tell us here is we're using floor instead of ceiling, because we want to end up with, if we did ceiling, we could get potentially more samples than there are available to us. So we're going to do floor instead. And then simply what I've shown here, right? So we've got, we can fit this, we can do this analysis 126 times in this audio signal. So what this means then, we're going to have a moving window that's going to go throughout. We're going to do a loop here. And we're going to do this 126 times. The exact same process that we've just done for the one window. And then we're going to add the results together using exactly what we've done here. The overlapping portion multiplied by these two half-hand windows, okay? Now, this is going to be really quick. Boom, done. Okay, so we've already done. There are easier ways of dealing with the little bits at the end. So we haven't done all of the samples because we did floor, right? So we've got some samples at the end that we haven't addressed. There are more sort of elegant ways of dealing with this, but for time's sake, we're just going to make those 0. There isn't any speech there anyways, so we're just going to make this 0. Now, let's first remind, I'm going to do this backwards. I'm going to, so let's say, first look at the spectrogram of the original audio signal, right? So that is MRI data, data 3. Yeah. Oh. Okay. Reminding ourselves, that's the spectrogram of our gross noisy signal. Now we compare this to what we've just made, the clean signal. Not bad. Not too bad. We can still see some little bits in there, again, because we can't get a perfect, an absolutely perfect estimate of the noise. Also, let me just ask, does anyone, I'm just gonna plot the first, I don't know, let's say 4,000 samples. Okay. Quick check of how we've done this. Does anyone want to take a stab at why the beginning of the file is exactly 0? We have literally no information, no amplitude at all. It is perfectly 0 for just this first bit.
It's the signal that you subtracted from.
Precisely, right? So we have an imperfect estimate of the noise, except for one window, the very first 1,024 samples. We have a perfect estimate of that because that's exactly what is there. We know exactly what that is. So we have a perfect estimate of that. Ideally, this should be 0 throughout the entire file, except where there is speech information. But we're not going to get that. We can only get that for just the beginning here. So if we listen to this, so again, let's listen to our the original audio, right? Data 3 audio. Create a sample object with that and play this.
This is an example of what noise reduction can sound like.
Okay, now let's listen to the clean data.
This is an example of what noise reduction can sound like.
Not too bad. It's not perfect, but it's usable, right? This is not too bad. Now, somebody mentioned like what about the zeroing, and again, I thought it wouldn't even be possible for us to do the inverse Fourier transform without it, but it turns out it is. So we're in uncharted territory for me here. Let's just go ahead and try this without doing that and see and hear what the results look like. So, okay, let's remove that. Right, okay, so it does it, but it's not as good. So this is with zeroing out. This is without zeroing out, and it's clearly not as good. Let's hear what it sounds like.
This is an example of what noise reduction can sound like.
Yeah, it's just not as effective. So there's your answer, is we zero them out because it works better. All right. Good. Okay, so yeah, so that's all I wanted to get to with this. Hopefully, even if you don't ever do spectral subtraction, the idea here is that these are where we're using techniques, digital signal processing techniques that are similar for these first two exercises, wildly different problems, but hopefully you can begin to understand what the concepts are here. All right. Any questions? I think I'm done with my bit. Molly is put in here. Negative values aren't here, but you see negative decimal values on a power spectrum is showing. Yeah. So decibels is a relative scale. Oh, say first of all, what is shown here on the spectrum is these are not decibels. So I haven't done any log transformation or anything. So we just showed the actual the raw amplitude here. So like one can have negative temperatures, one can also have negative dB. That's right. So you can have negative values for amplitude. That's perfectly fine. I've just gotten rid of those here. That's perfectly fine, Molly. I figured that was probably the case. I'm really glad you're here, though. Anyway. All right. Any other questions, comments, what things you want to go over? How were the Emma EMG data generated in the beginning? Is a simple list of vectors. So what do you mean by generated? So we've got so we've got this data here. Do you mean like in like, so if we look at, for example, so if we look at the lateral pterygoid, but this is just a single dimensional vector. Same thing with the medial pterygoid. But for the Emma data, we've got a matrix, and with hopefully, you know, informative headers here. So we've got 3 dimensions for each of these sensors. We've got for the tongue tip, the tongue midpoint, and the tongue dorsum. But then we also got these additional derived data of an estimate of we had jaw sensors on as well, of what the rotation of the jaw is, and then also what the independent dimensions of jaw rotation and jaw protrusion. But the rest of the data should look hopefully similar to you for anyone who's worked with Emma. We have 3 dimensions, X, Y, Z, of information of position information here. I haven't included the angles, but of the position data for the individual sensors. Yes, feel free to, if you have questions and are comfortable unmuting yourself, feel free. That would be helpful. Actually fit that into 2 hours. Can't believe it. Hopefully it wasn't too lightning quick. You can see why I wanted to put a lot of information in, and you can see why it was absolutely imperative to at least go through reading through the tutorial beforehand, because otherwise you'd be completely lost in what we're doing. But hopefully by at least going through and making yourself familiar with the exercises and the structure beforehand, then going through it at this speed should at least be digestible. We're going to do the same thing tomorrow, by the way. So if you have not looked at the tutorial information for tomorrow, please do so, because we're going to have the same format for tomorrow as well. No questions. You're all DSP pros now for 1 dimensions.
I wouldn't say pro, but you did a really good job explaining it, so I feel pretty good.
Good, awesome. That's the goal, right?
Yes, absolutely. I'm going to jump in here and say that this was great and very informative, and something that I haven't really worked on. And perhaps now people that have the, you know, they have the material, they have the explanation, and now can try the exercises by themselves. And even maybe tomorrow might, you know, at the beginning, we might reserve like a few minutes to see whether, you know, 1 day later, after kind of maybe going through the material again, people have come up with some more questions.
Yeah, cool. So on that, actually, a couple of things I want to note. It would be really beneficial for you. We're not going to go over it necessarily, but it would be beneficial for you to do that first exercise with all of the different signals. And another thing is go ahead and have a play here with changing the FFT window length. So the FFT window length, I've said, you know, we're going to use this one here because it's commonly used, but it's not the only one that you have to use. And you're going to get different results for the spectral subtraction depending on the window length that you use. The longer the window length, there are 2 things that happen. One, you get more fine-grained frequency information. So here, with a window length of 1024, each bin is SR divided by FFT length is 15.5 hertz wide. So a longer window length will give you greater frequency information. So if we did instead, we did like, I don't know, 2048, so double that. Each frequency bin then is half of that. So you get greater frequency resolution. But the trade-off is you're using a longer time window, right? So there's always a trade-off between frequency and time. You know this by working with wideband spectrograms and prop. Depending on the window length that you use, you either get more frequency information or like more usable frequency information because it's less smeared, or you get more time information, but you can't have both. There's always a trade-off. And go ahead and play with that here. So by playing with the FFT length, you will see the effects of having like using this trade-off and benefiting one dimension over the other. So if you create a smaller FFT window length, you will get greater time resolution at the expense of frequency resolution. And conversely, by having a longer FFT window length, you will have greater frequency resolution at the expense of time resolution.
We do have another question in chat. Before you address it, because I see people, it's 4, right, and people are starting to leave. So just a quick reminder, I put it in chat as well. So tomorrow there will be the second part at the same time, so 2 p.m. For Central Europe. Well, anyway, same time as today, but different Zoom link. So you should have received both links already. So just keep that in mind. And yes, there is a question in chat. Chris, I'm not sure.
Yeah, so this last one, it's an excellent question, and there are 2 different answers for the beginning and the end. So the beginning, everything is blank because so again, the goal here is you want to take the signal and you want to subtract from that the spectrum of the noise. Well, how did we generate the spectrum of the noise? From the first 1024 samples. So our first, we go through here in the loop, right? So if bin is equal to 1, what this means is that our samples here are defined as this, which are exactly one to 1024. What this means is that the very first time we go through this, or the first 1024 samples are going to be mathematically identical to our noise estimate. Why? Because the noise estimate was from these samples. So if we subtract them, we will get exactly 0 throughout, right? We're going to get non-zero for any other samples because we haven't looked at them yet, right? Now at the end we have zeros simply because we made them zeros just for simplicity's sake. We made them zeros because we can't. We're trying to figure out how many times can we do this, have this moving window throughout this whole time series. How many can we fit in? Well, it's very unlikely, it's highly improbable that you're going to get exactly the number of samples that gets you to right at the end of your signal, to the exact sample number. More than that, more likely than that, you're going to have either fewer or more. We don't want to do more because we don't have samples there to do anything with. So instead, we do less, we do fewer. And that then leaves us a remainder. What do you do with the rest of those samples? Well, the proper way to do this is actually to just do one last window and figure out what your tapering function should be for just that end. But for the sake of the tutorial, we just made them 0, just easy. But that's why there are zeros at the beginning and the end for 2 different reasons. Great, awesome. Great. Well, I will see you all tomorrow then. Tomorrow, we're going to be, we're working with, like I said, 2-dimensional data. So we're going to be working with actual magnetic resonance images. So we're going to be doing very, very different things, but hopefully my goal here in presenting it the way that I have is that you should start to see some of the commonalities behind the general approach that would take to some sort of signal, be it one-dimensional or two-dimensional.
Awesome. Thank you so much.
Great.
And great. So see you all tomorrow at the same time as today. And I'll
Great.
stop the recording.